Welcome to the final lecture. It's the last week of the semester, and this is hence the final lecture. We are going to talk more about quantum networks and how to prove that they don't have classical realizations in the sense that we talked about last week. As last week, we are going to be looking only at triangle networks, but everything that's being said here can be extended to more complicated networks. And in fact was extended and proved to be the case. Very well. So our basic scenario of the triangle network . And the method that we are going to be using or describing today is called the inflation hierarchy. So this is going to be something that's going to be reminiscent of the symmetric extensions and the DPS hierarchy, but now we have to do it for the whole triangle network, which is a nonlinear situation, so there's going to be some modifications. The idea is somewhat similar, or it will look somewhat similar, but there are some crucial differences. So the basic idea in the network was that we have three parties, Alice, Bob, and Charlie, and they are receiving some information or something from three sources, alpha, beta, and gamma, where alpha is connected to only Bob and Charlie, beta is connected to Alice and Charlie, and gamma is connected to Alice and Bob. Now, what was the idea behind the classical realization, or what was the idea of the experiment? What is the output of this experiment? What's the data that we get from the experimental physicists?
Do you mean that we could realize that we always have the same, or always the same if we have, okay, this was quantum mechanically, or we have always one or always zero, but it wasn't possible to have, like, for instance, two things with half the...
Yes. But what was this thing that can be always zero, always one, and not the convex combination of those?
So, like, it could only be always zero or always one if all of them always just signal 1, 1, 1 or 0, 0, 0.
Yes. But what's this thing that was always zero or always one?
I don't know what.
Yes. Okay. So I was asking is like the thing that we have access to is this probability of PABC of Alice outputting A, Bob outputting B, and Charlie outputting C. So this is the output of the experiment. Like, somebody does this in a lab and they come to us and tell us, like, we observed these numbers, go nuts, do something with this. Okay, now what was the classical realization? So we said that if this has classical realization, then that means that these sources can be considered to be just sending out classical information. And then we had a formula for this. Do you remember what that was? Or can you derive it on the fly?
What case again?
Classical realization. So if we have classical realization here of this network, then this PABC was equal to some expression. Yeah.
Integral over alpha, beta, and gamma.
Yes.
So, A to the beta and gamma and so on. And then here also
And what was the meaning? So I think the meaning is more important because I have terrible memory. I never remember formulas like this, but I remember the way how to write them, like what was, what's going on in them. So, okay, we are integrating over alpha, beta, and gamma, which are the possible classical values that these sources can generate. This P alpha, P beta, P gamma, what are they? So this is the probability that the source alpha will actually output the exact value alpha, and we are abusing the notation because this is here alpha is the source, and here it's the value outputted by the source of the same name. This is the probability that source beta will generate the value of beta, and this is the probability that source gamma will generate value gamma. This is a conditional probability that if Alice obtains beta from source beta and gamma from source gamma, she'll output A. Okay, so this is what the sources are doing, this is what the parties are doing. Now, on the first lecture, we were somehow discussing what is classical and what is quantum, and I somehow said that there's like a very clear distinction or some kind of very intuitive idea about how to define classical theory. Does anybody remember that? What is something that we can do with classical information and not with quantum information?
Copy it.
Yeah, exactly. Once we have quantum internet pirate, they will not work anymore. So what we can do with classical information is that if we have a source alpha here, it can send the generated random number according to this probability distribution to Bob and Charlie, but it can also send it to somebody else, you know? We can store it or something. This will not work with quantum states, because if this would be a quantum source, it would generate a bipartite state, and one half of that must go to Bob, other half of that must go to Charlie, and there's no third half to go to somebody else, okay? Now, the inflation hierarchy will be a hierarchy, so it will work, you know, it will be like a hierarchy of ever harder problems to solve. But first of all, we'll start with the lowest non-trivial level of n equals to 2, okay? And the idea here is that instead of having a network like this, we can duplicate all of the sources. Or maybe I go over here so that I have a huge whiteboard. So instead of having one source beta, or no, this is the source gamma, we'll have a source gamma 1 and the source gamma 2. Instead of having a source beta here, we'll have beta 1 and beta 2. And instead of having source alpha here, we'll have two of those, alpha 1 and alpha 2. The legends of old say that Miguel Navasquez invented this while walking around Beijing, because he had nothing to do, or something of sorts. So we have sources and we can duplicate them. So far, we can also do this with quantum sources, because if you have a source sharing a bell pair between Bob and Charlie, you can also have two sources creating bell pairs and sending them to someone. So now the idea is, how are we going to connect this to get a bigger graph? So if we have a source that generates alpha 1, like which of the parties there can receive something from alpha? So alpha generates something here. Which of the parties can receive something from alpha, or know what to do with the input alpha? Yes, Bob and Charlie. So if we generate alpha 1, we can have here instance of Bob, instance of Charlie, and send that to those, okay? If we generate alpha 2, we can also send that to Bob and to Charlie, and now we have to see this as different copies of Bob and Charlie. So this is the Bob receiving from alpha 1, and this is the Charlie receiving from alpha 1. Now, Charlie needs to also receive from beta, and Alice needs to receive from beta here, and also there needs to be Alice here receiving from this, and receiving from this, and receiving from this, and this, and this, and this, okay? So far, this is completely trivial, because this is just this network, but twice. So far, you can do this with, like, if I would tell you that I have this network and it has quantum realization with quantum sources and quantum measurements, you can also do this, because it just means that you now have two completely independent networks. So now here's the idea. We need to use the cloning of classical information to connect the inner and outer networks. And the idea is that, wait, we have a source alpha 1 that's sending something to Bob and to Charlie, and we have beta 1 sending something to Charlie and Alice, but also we can have a case where alpha 1 duplicates this information and sends it to Charlie here, but this instance of Charlie will be receiving something from beta 2. And the same thing can happen here. We can have Charlie that's going to receive something from alpha 2, but beta 1. Same here, we can have two more parties and two more parties. And we want to connect them like this and like this. And here we want to go like this and like this and like this and like this. So now we have parties A11, A12, A21, A22, B11, B2, B12, B21, B22, C11, C12, C21, C22. Okay? With classical sources we can do this. The argument why we cannot do this with quantum sources is that we are now copy pasting or sending multiple. We're copying here and distributing the output of the classical sources, which we cannot do with quantum sources. But the price we pay is that now we don't have Alice, Bob, and Charlie, but we have like 4 Alices, 4 Bobs, and 4 Charlies. Still, given stuff like this, it is intuitive that we can realize stuff like this, right? Okay. So the output of this experiment, if we would be to do it, we are going to call that, maybe I write it here. We're going to call that Q2. The 2 stands for every source is duplicated, but just has like 2 copies of each source. And it will be a probability distribution. It will be probability distribution on what variables? So here, the output is a probability distribution, and if we have classical realization, well, it's always a probability distribution of 3 variables, and if we have classical realization, it looks like this. But also, if we would do this with quantum theory, it would be probability distribution on like on triples of ABC. If we do this, we have, instead of Alice, we have 4 Alices, 4 Bobs, 4 Charlies. So what will be this probability distribution on?
Ij, Bij, Cij,
Yes. And now here's the question. Given that this is the classical realization of this network, what will this be equal to? Yeah?
Like, we would have to do pretty much the same, but a bit more. Like, we have then the alpha 1 for then beta 1, gamma 1, and so on for all possible cases we shown for the alpha, and for AB, and then and then it goes on and on, not for all, and then in the end we have E instead of alpha, beta, gamma, and we will probably have alpha 1, alpha 2, beta 1, beta 2, gamma 1, gamma 2 in the end. But yeah, pretty much the same, it's just way more, and only the possibilities used that are actually on that are actually those lines and so on.
Yes, exactly. Here I also need what?
Then you would need the last one missing, it's C.
Yeah, that's C.
You have it already, okay.
Yeah.
Yeah, that would probably just be alpha 1, alpha 2, is it alpha 1, then alpha 2, then beta 1, beta 2.
That's 6 integrals. Okay. So given that, we can compute this. Okay. Now, here's the thing that we need to do now. What we have done is that we have assumed that PABC has a classical realization, and we have derived that means that some kind of huge object exists, something way bigger. Now we want to get some kind of constraints that always hold for this Q2, only expressed in terms of this P. And now, I mean, please let me know if you get confused about P's, because this is a P and this is like everything in here is a P, and this is a horrible abuse of notation, but it's usually like understandable from the arguments what's going on. But also I would maybe advise that it might be nice if you do this in practice to put here a lot of indices, you know, because once you start putting here explicit values, it gets very easily very unclear. So now we need to start deriving conditions for this that we can express in terms of PABC. And then we are going to try to get something by saying that, okay, if PABC has classical realization of this form, then something must exist that has certain conditions that we can actually check. Right? Is the idea clear? It's the same as entanglement detection and all of these things. And the first constraint that we get is that what we have here written down should be invariant with respect to exchanging these two sources. Because they are completely arbitrary copies of each other and they should be doing the same thing. So if we exchange them, we should get the same thing. So what would happen if we would exchange beta 1 and beta 2? So now if I want to I mean, it was over here, so it's slightly wet. If I want to exchange beta 1 and beta 2, what's going to happen is that the sources in here are going to exchange themselves, and then I can do substitution to get everything back into the original form. But somehow I introduce these indices in such a way that this number corresponds to this one and this number corresponds to this one always. Which means that if you do all of this and you exchange the sources beta 1 and beta 2, what you're going to do is that you are going to exchange these two numbers. So this one would become 2 and this one would become 1. And you are going to exchange these two numbers because this one would become 2 and this 2 would become 1. The same happens here for the C's, although it's on the other index. Because now for the C's, this is the index that corresponds to alpha and this is the index that corresponds to beta. So for C's, what would happen is that this 2 would switch with the 1 and this 1 would switch with the 2. We can write this down explicitly and we get that the Q2 of A11, A12, A21, A22, B11 to B22, and C11, C12, C21, C22 must be equal to Q2 of the stuff where we switch the indexes, which corresponds to switching the sources. So A21, A22, A11, A12, the B's are not connected to beta, so it's the same thing. And then we get C12, C11, C22, C21. And this we get by switching beta 1 and beta 2. Now, you must understand that this is not a single equality. This should hold for all possible values of A11, A12, B1, and for all of those indices, okay? So if you would want to enumerate this, you should plug all possible combinations behind these indices, and you get that some element of Q2 somewhere must be equal to other element of Q2. We can do the same with switching the gamma sources, and then we get that Q2 of A21, A22, A11, A12, and now we actually start, sorry, reading the wrong line. 1, 2, 1, 1, 2, 2, 2, 1, and now we actually get B21, B22, B11, B12, and the C's are left invariant. And this is what we get by switching gamma 1 and gamma 2. And we also get something for switching the alphas. Now the A's are left intact, but the B's and C's get shifted in the same way. And this is what you get if you switch alpha 1 with alpha 2. This is nice because this we can check even if we don't know what we have here in this formula, right? I can always check whether, I can always try to look for a probability distribution on many indices that has this kind of symmetries. Is this enough or not? Yes?
Maybe it is, but one thing I could imagine what could also be necessary that we like switch the betas and the gammas, or the betas and the alphas, and so on, and each time 2, and then in the last time all 3, and then each possible switch around. But I don't know if this is, or what this could also be not necessary anymore, but it will also have to hold.
Yes, you're completely right. And the trick is that if it holds for switching alphas and switching betas, then it holds for switching alphas and betas.
Yeah, okay, that's true.
Yeah. No, that's completely okay. This is also something that we had in the symmetric extensions. In principle, you should enforce like symmetry with respect to arbitrary permutations, but I said like neighboring swaps are sufficient.
Yeah.
So but I mean, good thinking. In that sense, this is enough. But okay, so now if I give you this PABC, coming for example from the elegant joint measurement distribution, is this condition enough to check whether it has classical realization or not? At least in principle. So what would we do is that we would say that, okay, somebody measured something, so we are given this PABC, which comes either from theory or experiment. And now we know that if this has classical realization, then Q2 must exist with this form. So now we can say, like, we can ask our computer or some kind of oracle or a PhD student or someone to find or slash check if there exists Q2, which is this huge probability distribution, such that Q2 has symmetry that's specified over there, which is coming from these alpha 1 exchanged by alpha 2 and so on. Beta 1 exchanged by beta 2, gamma 1 exchanged by gamma 2. Okay? Looking for a probability distribution that satisfies some conditions is an instance of a linear programming problem, which is something like semi-definite programming problems that we had before, except for this linear programming is actually easier because your variables are not positive semi-definite matrices, but they're just vectors with positive entries. So, is this a good check or not?
The only thing I can think of, but it could also, is like we know we can switch them around, but I don't know if we know that they are the same.
Well, I mean, what do you mean the same?
Like what I can imagine trying out, I don't know if it makes sense, but like the one I can switch around, that for those that I just say, okay, and on the one side I just set them the same, and are they the same as if I didn't set them the same? I don't know.
Well, I mean, if you enforce that this is equal to that and equal to that and equal to that, then they will be exactly the same. Like the actual number that's... Because in the end, this just tells you that many components of the vector Q2 are going to be the same numbers.
Yeah, but these are just ideas, what could I try? And I can't think of much more.
Okay. If we now, okay, so let's imagine we fix something. For example, this PABC will be 1/2 0 0 0 plus 1/2 1 1 1. It should not work because we know that it doesn't have classical realization. I do this and I tell you that yes, Q2 satisfying this symmetry conditions exists, or these conditions that we have here exists. What does this tell you about P? If I tell you that Q2 for some PABC, the Q2 does not exist, what does it tell us about P?
Is it something like, again, okay, if it works, we know nothing, and if it doesn't work, we know it doesn't work?
Yeah, it's the case when it doesn't work, it works. Yeah. Yes. That's going to be the idea that if Q2 doesn't exist, then we know classical realization doesn't exist. But here, if I tell you that Q2 does not exist, does it tell you anything about P? What is the relation here between Q2 and P? What is the relation between this column of numbers and this column of numbers, according to the conditions here? Is there a relation according to the symmetry conditions? So here we have the symmetry conditions. Do they in any way relate Q2 with this PABC that's coming from the experiment? So this is Q2 of something, and we are checking whether this exists. So it does not depend on P, right? Because we are just, this is our variable over which we optimize, or something which we are trying to find. This is Q2 with permitted indices. Does it depend on P? This is also Q2 with permitted indices. Does it depend on P? This one? So far, this will not tell you anything because there is a relation missing between this thing that we have and this thing that we are looking for, whether it exists or not. This will just tell you that, yes, you can have probability distributions satisfying these symmetries, but it's rather easy because just take like Q2 of everything being 1 over a number of variables, so constant probability distribution, it will satisfy any symmetry that you want. So it will always exist, and it doesn't tell you anything about this P because they have completely no relation between each other. So what we need now is that we need to find more constraints here that would actually relate this Q2 with this P. So we can go back to the definition, to how we constructed the Q2, and now from this we somehow need to extract how to relate Q2 with P.
Like you already put it sorted on the blackboard, and I would say, okay, maybe a relation between first all the A terms with the A with the condition beta gamma, and there we can maybe find something, and all of these have to be the same as P R alpha beta gamma, and then the second thing and the third thing, and like.
So you're thinking about these terms?
Yeah, I'm thinking about these.
Okay, but the problem is that we don't know whether these these things are because we're looking for them.
Like, I'm just looking for starting points.
Yeah, but very good, very good, very good. Okay, so there's two ways to do this. You can either see it in the picture or you can see it in the integrals. Which one do you consider more intuitive? Pictures. Integrals. Okay. And you?
Maybe depends on how the pictures.
I would say picture.
Okay, like this is the picture, so.
Yeah, it's alright.
Okay. So here we have 6 integrals where we integrate over 6 variables, and beta 1 is in here and in here, and it's also going to be somewhere here in the C's, and also, so for example, gamma 1 is in here and here and here. So it's like, so this function, this subintegral function, when you look at it, it's product of many different functions, but in the end, when you write this down, it depends on all of the variables over which we integrate, right? So we cannot like split the integrals into more integrals. But if we would be to get rid of this term and this term, what would happen? Like, now imagine that I just erase the A12 and A21 term, and B12 and B21 term, and C12 and C21 term, and I'm just left with A11, A22, B11, B22, C11, C22. What's going to happen to the integral? So I'm saying that we should maybe look at the integral of this form P A11 given beta 1 gamma 1 P A22 given beta 2 gamma 2 P B11 given gamma 1 alpha 1 P B22 given gamma 2, alpha 2, BC11 given alpha 1, beta 1, and BC22 given alpha 2, beta 2, and there's the probabilities of alpha 1, alpha 2, beta 1, and to gamma 2, and D everything.
Then I guess we could like have one integral times another integral with all the one parts or the two parts, just
Exactly.
pulled outside one another. But yeah, the other thing we just have to figure out.
Oh, sorry.
Two, you can just write two parts or something.
Of 1, B, beta 1, B gamma 1, B this, D that, D last one, so this is the bracket, times the other term. Very good. What's this?
It looks the same as the other two.
And if it looks the same,
like you say, those are just variables, we can rename them.
well,
Like if it is like this, then we said if it has a realization like this, it's classical.
yes,
So it's classical, and maybe you want us to get to the point that maybe if all those, I'm just gonna say interaction, they are not interactions probably, but all the 1, 2 parts, they are just one. And in the end, if they all fall away, if we can actually pull it apart, then it's probably also it's possible to realize it in classical.
yes, okay, you're like 2 steps ahead. No, but that's very good. I just want to like do the steps in between explicitly. So what's this equal to? It's exactly this integral, which is different variables. So this is just P A11, B11, C11. And that thing is going to be the same with 2. So this is just P A11, B11, C11, P A22, B22, C22. Okay? Now there's two important things. The first one is that this is polynomial in the input data, which is going to be important later. But you know, it's like P times P, so it's like a square or something. It's a polynomial, so just keep that in mind. Good. Now, is this enough? Can I now write a condition based on this here?
If you outside this, probably not. Like you already said, it's like they are multiplied together, so we have to get something rid of that.
No.
But I have to do something to work around it.
No, that's not the problem, because we know exactly what PABC is. So we can evaluate this product. So yeah. But how did I write down this integral? What I said, like, you know, Q is defined according to this integral down here. That has all of these terms. And I say, let's drop these terms, which we can. We get this integral, and that's related to the P. But now the problem is that this integral is not the same as this integral. So if I want to use this as a constraint, I have to relate this integral to that integral. And I cannot write a constraint that write everything down, cross off some terms, and then integrate that, and you're going to get P squared. So how do I get rid of this one term? There's 6 terms I want to get rid of, and I can do it one by one. So what is this P A12 given beta 1 gamma 2? What do we know about it? where does this thing come from? Where did I get it from? So now I want to like rewind yourself in your mind, because when I wrote these integrals, like all agreed that this is what the correct thing to write. Now I'm asking, like, why did I write this here? Where does it come from? How did I get this? I assume that PABC has classical realization, and I said I can write this down. So I must get this from somewhere. What is it? Where did I get it from?
It has almost lines from which, like, I find it hard to say in English. Like the different types of lines you wrote and stuff, as you drew down, and it's always like, okay, all these are for the different types of sources for, I guess, for A, I, J, for A, J, not the same, not equal.
Yeah, so this is the probability that Alice 12 will output A12, given that she receives beta 1 and gamma 2 from the respective sources, okay? So this is a conditional probability, this one. Where am I getting that conditional probability from? So I can only get it from here because I only assumed that I have this. Or I must prove that it universally always exists. So but I can tell you I'm getting it from here. So where from here am I getting that PA1 given beta 1 gamma 2? So it must be either the three integrals, or one of these three terms, or one of these three terms, or one of the three differentials. So the question is that when I was writing down this expression, you all agreed that I can write down this expression because I know this thing. I know that PABC has classical realization, which means that I know that there is a conditional probability on Alice, conditional probability on Bob, conditional probability on Charlie, probabilities for the sources, such that they reconstruct the probability I have. I said that if that's the case, we can draw this type of bigger network, and we can compute the probability there, and we can compute it like this. And when I was writing down this, I said that if Alice 12 receives beta 1 gamma 2, she will output PA12 with this probability. I'm just asking, like, where did I get this from? So you can see these conditional probabilities as some kind of recipes for Alice 12, what she should do. Like if she receives 0 from beta 1 and 2 from gamma 2, she will output something with some kind of probability, and this thing tells her with what probability she should do it. So it's like a recipe, like it's a program, if you will, that she will follow. But where did I get the program from? How did I know that, you know, do we have something to write there?
Like it's the sources from which Alice A12 got the information, even like picture.
Yeah, but okay, so
they don't know where you're going.
yes, okay, I see. So it's exactly the same as this thing. Yeah, okay. So the question was too trivial. So what do we know about this thing? What are the constraints on this thing? Yeah?
It lies between 0 and 1.
Yes. And it's a conditional probability, which means it's a probability distribution in A given the values of beta and gamma. So what is the thing that must hold for all probability distributions? What?
It sums to 1.
Yes, exactly. One and exactly one, because probabilities have to be normalized. A nice way to think about this is that something must happen and exactly one thing must happen. Okay, so what if I would just write times 1 times here?
It's what I said.
Yes, but I said that you are 2 steps ahead. We just need to do...
I thought you didn't want to hear it because it's already there.
Yeah, no, sorry. I wanted to, I just want to take it slow and systematically. So if we write 1, we can write 1 in this form. So we can say that this is the sum over P, A12 given alpha 1, beta 2, so over that red term over there, and we just pull out the sum out of the integral. Okay? And we can do that for all of those 6 terms. So we can say that, well, in this case, Then we get some kind of sums here, and we here get integral that's going to contain all of the terms that are in this integral now. So we just get that this is the sum over a12, a21, b12, b21, c12, c21 of this q2 of a112, c22. Aha! But this relates q2 with the p. So now if we are going to be looking for q2 here, it has some kind of relation to the input data, so it's going to tell us something about the input data. Very good. And this is the first level of the inflation hierarchy. Now we can pull out our computer. We can take some kind of PABC, for example, the Fritz distribution. We can say that we are looking for a probability vector Q2 that satisfies all of this symmetry constraints, and we can spend the whole night implementing all of those, or maybe less, depends on how smart we are about it. And we implement some kind of sum up constraints because we know what PABC is, and for the sake of this calculation, PABC is something fixed, so we can compute all of these products. And we can just say that, okay, if you sum up the entries in this, you're going to get stuff like that. And then we can, for example, check if such Q2 exists for a given PABC or not. If it does not exist, means that that PABC does not have classical realization. If it does exist, we can say that, okay, it didn't work for duplicating the source, so we can, triplicate? We can, instead of having beta 1 and beta 2, we can now add another source here, beta 3. Instead of having 4 parties, we will now have 9 parties because they have each 2 indices, and the index runs over all of the sources. We will again have symmetry conditions corresponding to exchanging all of the sources, but now we have to do beta 1 and beta 2 and beta 3, and so on. You can again simplify this by the neighboring permutations and things like that. And we again have to derive some kind of conditions in this way, where now we are going to have p times p times p, so it's going to be a cubic polynomial in the input data p. And then we can also do that for n sources. And we can hope that at some point it's going to rule out classical realization for our input, or for the given PABC that we were given from the experiment or from theory. Now, before we proceed any further, I want you to see what we did here inside the graph. So we did it with the integrals. I said we can also do it with the pictures. Now we are going to do it with the pictures. And with the pictures, the realization is that if we just take this one, and this one, then they form a triangle. If we take this one, and this one, then they form a triangle. So if I sum over all of these Alice's, Bob's, and Charlie's that are not circled by some color, I get exactly 2 triangles that I actually had there before when I started drawing everything. And saying that these 2 triangles must be the same as this triangle times itself, will in the end just be this equation. Very good, and this is how inflation hierarchy works. Now there's a nice thing, there's a theorem that one can prove. And you can find this theorem in the paper by Navasquez and Wolf. But they actually prove it for general network, not for triangle network, but they oftentimes use examples from triangle network, so we can find a lot of there. And this theorem is a convergence theorem, and it just tells you that if Qn exists, so if Qn exists, then what's the exact formula? Then the P ABC that we are given is something like of the order 1 over square root of n away from having classical realization. Okay, so if you, for example, come to me and tell me that you took some PABC and you checked this for n equals 1 million, and the Qn 1 million exists, then I can tell you that, okay, that's very good, because now we know that your PABC is of the order 1/1000 in some kind of metric from the set of classically realizable probabilities. And if you take n to infinity, then this becomes 0, and then that means that if you check inflation at every level, then PABC must have classical realization. So in other words, the hierarchy converges and so on. Very well, this somehow means that we cannot fundamentally improve the hierarchy by writing a better one, and it actually converges to the set that we wanted to converge, because it converges to the set of classically realizable probability distributions. So what's the problem now? I said that deciding whether a given quantum realization of a triangle network has a classical realization is a very hard problem. And this seems to work always, you just need to check it for a higher end. So what's the problem? Yes?
The computation.
Exactly. Because you see, you are going to have a lot of Alice, Bobs, and Charlies. There's going to be a huge probability vector, and at some point your computer is going to tell you, like, sorry, I don't have enough memory to even consider this problem. So in practice, n equals to 2 is fine, n equals 3 goes, and I heard of someone doing this for n equals to 4 for a triangle network. So there's two things. Either we can now start thinking harder and just try to add some kind of extra constraints to make the convergence better, or at least to make the things that we can do numerically better, or we can just figure out the new methods to work with triangle networks. I can tell you about the first thing because I don't know anything about the second thing, and nobody does. Is this color like visible?
Yeah.
Okay. So the first thing that we can start doing is that here we decompose the big triangle, the inflation of the triangle, because the big network that we have here would be the inflation of the triangle network. We decompose it into a product of the two triangles. Now we can also do this in a different way. And the one way to do it is to take just this source connected to here, to take this one, just connected to here, and take this one, just connected to here, and sum over everything that's not brown. So in this case, we get that there will be sum over A11, A21, A22, and the same for B's and C's of this Q2A11 to C22, and this will be equal to something. Now, there's two ways to find out what this is equal to. You can either see it from the picture, or you can plug it into the integrals and beat up the integrals until you get the correct answer. Of course, if you want to prove it explicitly, you should do the integral part, but at least for me, it's a little bit easier to see it from the picture. Oh, I forgot the other legs. How come this one's not connected? So here the hint to write something here is that given this PABC, we can also define something like probability that Alice will output outcome A, and don't care about Bob and Charlie. How would we define this? So this is just given that we know what will happen in the experiment. So this is joint probability for outputs of Alice, Bob, and Charlie. And now I just want some kind of probability of Alice outputting A for whatever Bob does and whatever Charlie does. So it's just a marginal probability distribution.
It's just like above, but you omit some parts.
Well, if it has classical realization, yes.
Yeah, okay.
But now I'm asking, like, how do you compute it from this? Right? We just sum over whatever Bob does, sum over whatever Charlie does, and we just get this thing. And this thing was also the thing that appeared in the thinner inequality. And what you get here is that you get PA of A12, PB of B12, and PC of C12. Because in this huge integral, what you are just left is this PA of A12, beta 1, gamma 2 term. And then you can say that, oh, but that's the same thing as if there was some other Bob and Charlie over which I summed, okay? So you somehow take this Alice here and you say that, but I can actually put here other imaginary Bob. So that's Bob imaginary and Charlie imaginary that are connected here and connected by a source. But I have actually summed over these two things. And because I have summed over these two things, the stuff on the right-hand side will be just the marginal probability on Alice, and the sum over here is just summing over everything that's not brown and used to be white. And this is actually good, because we did here something non-trivial, because what we had up here is a second-order polynomial in the probability distribution. Here we have a third-order polynomial in marginal probability distributions. So this thing that we have here does not follow from the thing above, because you can also somehow draw the stuff differently, and you can say I sum over a different set of indices, and you can get here some kind of marginal probability distributions, but only two of them, at which point it would most likely follow from what we have up here. But since this is third order, it cannot follow. And also you can play with it and see that this is the only way to obtain something that's of a third order in the second level of the inflation. So then what we do is that we add the third order conditions here. And this is actually not in vain, or this is not useless, because there's examples where this actually does help. And again, if you go to this paper, they discuss these third order conditions, and there's a footnote where they say it helps, and actually go to an explicit reference, where if you add these third order conditions, already second level of inflation is enough, but if you don't add them, you have to go to the third level. Of course, in this case, we can go to the third level, but you know, usually you need to identify the highest level we can go to, and then add as many conditions as you can. Another thing that we can do is that we can change the inflation network and not draw it like this, but draw a different inflation network. So this one comes from the idea that we are going to be duplicating sources, and it was proved here that this actually converges. But the problem is that we are getting n squared copies of Alice, n squared copies of Bob, n squared copies of Charlie. And so there's a lot of copies of everyone. It grows too fast. So we can try to just do a different network, get conditions from that. Maybe for the other network, we'll not know how to continue the network to make it bigger, so we wouldn't be able to prove convergence theorem. But we in principle don't care, because anyways we stop at n equals to 4, you know? It's like proving what happens at infinity is nice, but not so much when you can go like 4 meters. So for example, one thing that one can do is the wagon wheel inflation. And what we will do now is that we have source Bob 1 here, we have Alice 1 here, we have source gamma here, and there's going to be just one of those, Alice 2 here, and there's going to be source Bob 2 here. We get Bob 2 here, connected to source alpha 1, Bob 1 here, connected to source alpha 2. We get, and here we get a lot of Charlies. So this is the so-called wagon wheel inflation. And it's still an inflation of triangle network. Because now if you sum over everyone, you get a triangle over here. If you sum over everybody over there, you get now a triangle here, and so on. You get many triangles. Moreover, we can consider like conditions like having, for example, this here, and maybe now we can consider like having these two sources and maybe something disconnected from them. So this one source and so on. You know, you can derive many conditions of this in this spirit and just check whether the given Q exists. But now somehow the good thing is that we have less Alice, Bobs, and Charlies. Now, the nice thing is that these linear programs, if you would implement this, they actually so every semi-definite program has a dual of itself, right? And we saw this, that for example, for the symmetric extensions, the dual was giving us some kind of entanglement witnesses of very specific kind. Also, these linear programs coming from inflation hierarchy, they have duals, and these duals are giving us some kind of conditions of a very specific kind, so some kind of witnesses. But because the linear programs are polynomial functions of the input probabilities, these inequalities are not linear, because there's going to be something like p times p or p times p times p in the inequalities. And so one can derive these inequalities, and it's nice having inequalities because then you can investigate some kind of noise robustness, but these inequalities are usually complicated. So if one would take the Fritz distribution, which was a triangle network thing where Alice was distributing classical information and Bob and Charlie were doing the CHSH experiment that we had last week, one can use the wagon wheel to actually find a witness for that, an inequality that's falsified. And it looks like this. So it's already like a complicated inequality. Now, this is not the optimal inequality because actually you can find a better inequality with higher violation, and that one you can obtain from this web inflation, and the respective inequality is this. So it gets kind of insane kind of fast. It's like this whole thing is stuff less than 0. Does anybody want to actually check it, or? So yes, you can obtain inequalities from this, but they're not linear inequalities, so they don't immediately work like entanglement witnesses because they're nonlinear. But this is to be expected because, as we already saw, the set of classically realizable probability distributions is not convex, so it cannot be bounded by linear inequalities. It must be bounded by nonlinear inequalities, because if it would be bounded by linear inequalities, it would be convex. Good. And maybe to wrap this up, I would want to show you one last thing, how to do something about constraints like this. So what I'm now going to show you works only if n is equal to at least 3. So for n equals to 2, this is going to be trivial. This is just something like a hint that if you ever find yourself implementing things like this, what is maybe a better way to implement this type of conditions? So we have this condition that if we sum over A12, A21, and the same for B's and C's of this, wait, sorry. No, I said n is equal to at least 3, so we must be summing over Aij such that I is not equal to j, and the same for Bij and Cij of, say, Qn, and here's Aij, Bij, Cij, and this will in the end give us a product over I going from 1 to n of P, Aii, Bii, Cii. Okay? It's the same as here. You sum over everyone that doesn't have the same indices, so that's exactly this sum, and you get products of the input data, which is just this. And you can see that this is polynomial of order n. Now, here's the trick. In this case, we don't have to sum over everybody that has different indices. We just need to sum over the parties that has different indices and corresponds to the sources n. So this is the idea. If I would sum over AIN and ANJ, and the same for B's and C's, such that I and J are strictly less than n of this Qn, what I would be doing is that for the nth source, I would be summing over every party that's connecting the nth source to everything else that's going on here, right? So I wouldn't split everything into product of n triangles, I would just pull one triangle out, and everything else stays connected. So what we get here is that we get something that we can get out of duplicating the sources n-1 times. So we can say that here we get some Qn-1 of, you know, all of these things times the input data corresponding to nn, bnn, cnn. Yeah. Is this roughly clear? Now you can either draw this explicitly for n equals to 3 and then you can see it, or you can write the integral explicitly for n equals to 3 and see it, or you can somehow try to do the manipulation in your head and replacing all of this B11, C11 and A11 by a subnetwork of many other Alice's, Bob's and Charlie's, and if we basically sum over these things, then we somehow disconnect the green network from whatever the yellow stuff would be. And that would be this. We still cannot use this as a constraint because we don't know what this is. We're optimizing over Qn, but we don't know what Qn-1 is. This would be the inflation we duplicate in n-1 sources. But the thing is that we actually can construct this because we can say that if Qn exists, then I can always define Qn-1 of everything as summing over Aij such that, so summing over In, Ajn, and the same for B's and C's, but now I and J can be also equal to n, so they're not strictly less than n, they're less or equal than n of this Qn, right? This is just to say that if you do inflation of the third order for triplicating the sources and you sum for everything that contains the index 3, then you're going to get inflation where you duplicate the sources. So plugging that here, we get that this is sum over the A-N, A and J, same for B's and C's of this Qn, and here's P of A and N, B and N, C and N. This is a new relation. And now the nice trick is that if you enforce this, by symmetry between the sources, you are also enforcing this, not having here A and N, but having here A, I, because the symmetry of this Qn is going to take care of that. Because if I enforce this for the source N, I'm enforcing that for every other source by permutation of the sources. But now you have to do like a triple permutation where you permute all of them. Moreover, if this holds, then I can use this as an iterative formula to prove this thing. So if I have Qn satisfying this stuff, then this follows as an iterative formula, because by summing over everything that contains index j except for the diagonal ones, you get one of these p's out, and then you repeat the same thing here by summing over, say, the stuff that has n-1 here, n-2 and so on, and you're going to be collecting more of these p's here. How many? Well, exactly this many. The fun thing is that in some applications, this condition is way stronger than this one, which I actually once found out like in a practice, because we were doing a project with a postdoc in Köln, and we were discussing how to program some kind of hierarchy. It was not this one, it was a different one, and it was not really working out. And I wrote some code, and that worked out. And then he wanted to somehow also implement it himself, so that we have so we both implement the same hierarchy and check that we get the same results, you know, because this is a big thing. There's you can easily do index errors and stuff like that. And he said that, yeah, I implemented it and I got way better results. I was like, how can you get way better results when you implement the same hierarchy? Turns out, instead of implementing this condition, he said yeah, it's going to be easier to implement this thing, right? in fact, it actually is easier to implement, or like less sums and things like that. He implemented this and got like mind-blowingly better results. So stuff like this can help. And also for all of these things where I said that you can obtain third order polynomials, you can still do something like this when you say that instead of here cutting everything and isolating all the three brown triangles, I just isolate one of them, where I assume that these things are marginalized over, and leave everything else. And you can get stuff like this also in iterative forms. And one would then hope that, well, you can then prove that it will work at least as good as this condition, maybe better. What could be nice is that this will give you more, like less conditions, then it could be easier for the software to implement and so on. So it's like a win-win situation because it's a strong, you're getting here stronger conditions and it should be easier to actually implement. So one should be on the lookout for conditions like this. They tend to work out very well. Yes, and with that, I'd like to thank you for your attention. If you have any questions, please feel free to ask. If you have questions later, send me an email. I believe this is the end of semester, so we are not going to see each other in this kind of way again. But there's going to be the seminar on the 25th of September. So everybody that's February, yeah. So everybody that's so far picked a paper, there is somehow preliminary time schedule lying on the desk over there. You can check and let me know if you need to be moved sooner or later, or if you have any requirements. If you haven't picked a paper so far, then just you can do it even the day before the seminar, but please start reading your paper in advance. It's not easy to do. And just come and you're going to go after everybody that's on the time schedule has already done it, right? Questions?
I have something else at the same day. Will we be required to spend the whole time there, or it would probably be preferable?
It would be preferable. It would be nice to everybody else, but if you have to go, you have to go. So
See how long I can stay.
yeah, then just maybe check the preliminary schedule
I
and.
haven't picked the paper yet, so I will
Okay.
be on there.
Okay.
Then I came up later. So when I voted for the date, I didn't know it. So.
Yeah, okay, no, that's fine, but then maybe pick a paper as soon as possible and in your pick write that when you can be on that day there or
Maybe
some constraints.
skip the other thing as well. It's the whole weekend.
Yeah.
What I will do.
Okay, very good. So thanks for attending the lecture and